All right, so now we have our last and final video for this section, and that is going to be on points of inflection, concavity, and the second derivative test. So one thing that we know is true is that if your slopes are increasing, so what that means is this slope here might be like 1 or 1/2, but notice that this slope here is steeper. So like the slope, the value of the slope is getting bigger. That means our function is concave up. Even if your function is increasing overall, if you notice that the slope, the values of the slope are decreasing, so if this was like 3 or whatever, and then you can see like, oh, this one is smaller in value, like my rise over run is smaller, so f prime is decreasing, then my function must be concave down. Same thing is true on these two graphs. So notice it has nothing to do on whether your original function is increasing or decreasing with concavity. It's whether or not your derivatives are increasing or decreasing. And so I personally like to expand this into what I call the fun chart. And so see how it spells fun? So if my function is concave up, then I know that my derivatives must be increasing. Okay? If my function is concave up, then my derivatives must be increasing in value. Well, I know from before, then its derivative, which would be f prime prime or f double prime, that would be positive, right? Because if a function is increasing, its derivative is positive, which means if you look down here on this test for concavity, if a second derivative is positive, then its function must be concave up. So this little chart is really, really helpful. If a function is decreasing, or is concave down, excuse me, then the derivatives will be decreasing, and those derivatives will be negative. So this is the connection from the first derivative test. And it helps us make connections between f prime, and f double prime. Now, the other thing just to note here is the same thing is going to be true with particle motion. If we end up having a question about that, where like if you know that this is your position curve and this is your velocity curve, then this is true for acceleration. Similarly, if this is your things you know about your position curve, then this is what you would know about your velocity curve. Okay, but this fun chart here is going to be your lifeline for figuring out all of the connections between these graphs. Now, when a point changes concavity, okay, we call that a point of inflection. So here we say that this graph is concave up like a cup, and then just when it changes to down like a frown, that is a point of inflection. When that happens, f double prime will be equal to 0. Okay, so kind of like when we did critical points before, but that's what we're going to be looking for changes in concavity is where do I have potential inflection points? And then we'll go ahead and do a number line test, just like we did with first derivative, but we'll do it with second derivative. All right, so determine all intervals where f is concave up and concave down. What are some points of inflection? And then we can use a graphing utility. So let's find f prime. 3x squared minus 12x plus 9. And then I need to find the second derivative this time, 6x minus 12. I'm going to set that second derivative equal to 0, add 12 divided by 6, and I get x equals 2 is my only potential point of inflection. So I'm going to test this on a number line, and I'm looking at f double prime. Okay, and let's go ahead and make connections all the way up. So we'll talk about f prime and we'll talk about f. All right, if I plug in numbers smaller than 2 into the second derivative, 0, for example, I'm going to end up getting negatives. So that means f prime must be decreasing and f must be concave down. If I plug in numbers bigger than 2, like 3, I'm going to end up getting something positive, which means f prime must be increasing and f must be concave up. Now this is what we want. Okay, I'm just adding in this little extra piece if we needed it, but this is really what we want here is concave up and concave down. So f is concave up from 2 to infinity, concave down from negative infinity to 2, and x equals 2 is an inflection point because there's a change in concavity there. Another thing the second derivative test is helpful for is if I need to figure out if a critical point is a maximum or minimum, and I really don't want to do the number line test. So let's do an example of this. Now, I always tend to default to the number line test, but the second derivative test is helpful in some situations. So let's go ahead and do an example here. All right, so I need both the first and the second derivative on this one, and I need to identify the critical points because I need to figure out first where f prime is equal to 0. So f prime is 5x to the 4th minus 15x squared. And I want to know what are the zeros of that function. These are, again, going to find me my critical points. So I'm going to factor out a 5x squared. I'm left with x squared minus 3. Oh my goodness, that should be a multiplication, not a subtraction. All right, so I get x equals 0. I get x equals plus and minus the square root of 3. So those are my critical points. I could put those on a number line and do first derivative test. Okay, that is possible for me to do, but let's go ahead and practice second derivative test here. So f double prime is 20x cubed minus 30x. And what I would like for us to look at is this box right here and then plugging in these values. Now, all I need to know is whether or not this is going to give me a positive result or a negative result. So let's go ahead and plug this in. I'm going to use a calculator just for time's sake. All right, well, I know when I plug in 0, I get f double prime of 0 is 0. So test is inconclusive. Okay, I don't know. So it's both potentially a maximum or minimum and a point of inflection. Like, is this an inflection point? Because the second derivative is 0, like we don't really know anything there. But let's see what happens when I plug into f double prime. Okay, I'm trying to figure out the signs of f double prime here. So what happens when I plug these in? 20 times negative square root of 3 to the 3rd minus 30 times negative square root of 3 gives me a negative. So I'm going to write that f double prime of negative root 3 gives me negative. So f must be concave down, and so x equals negative root 3 must be a local maximum. Right? Because if f is concave down and I have a horizontal tangent line there, then it must be a local max. All right, let's see what happens when I just change these to positive root 3. Okay, I end up getting a positive number. So f double prime of root 3 positive means f is concave up. Therefore, x equals positive root 3 is a local min. All right, let's go ahead and look at this graph and just see kind of what's going on at x equals 0. Like I know these two things are true. I know where the critical points are. Something funny is going on at x equals 0. I know I have relative max and min here. I know some concavity pieces here, but let's just look at a graph of this and see what's going on. Y equals x to the 5th minus 5x to the 3rd. All right, so let's plug this back into what we know from curve sketching and pre-cal. It is a x to the 5th function, so end behavior makes sense. If I factored out an x cubed, I would be left with x squared minus 5. So it makes sense that I have zeros at 0 and plus or minus root 5 with a multiplicity of 3, a multiplicity of 3 at x equals 0. So think about all of those things that we learned. I have zeros at those 3 places, okay? And when we've done some curve sketching, we've kind of just like gone through and been like, okay, I know I have to go up with end behavior and then a wiggle through 0, down, back up through 0, end behavior matches. But now we know more, okay? Now we know exactly where that high point and low point need to be because it has to be at x equals negative root 3. So we're gonna be able to put this all together with what we know from pre-cal and curve sketching, what we're learning about calculus and curve sketching, and really put together great graphs of sketches and then be able to verify those with technology once we get there.